in the sample space of S, okay, we consider that as the universal. Inside that there are two defined events, event A and event B. Now, if there is an intersection, then this would be this part, right? And that's what we call the intersection of A and B, right? The inverted U kind of symbol. And from last time we've learned that the probability of the union of A and B equals to the probability of A plus the probability of B minus the intersection, the probability of the intersection of A and B. Okay, so now if A and B are mutually exclusive events, then that means A and B have no overlaps, right? And in other words, probability of A intersection B is equal to 0. And so in this case, this vanishes. And so if they're mutually exclusive, then the two events would be separated like that, and there's no overlaps. And in other words, if A happens, that means B will not happen for sure. And if B happens, A will not happen for sure. So that's the concept of mutually exclusive. Now, when we talk about independence, there is no Venn diagram to show, okay, because they are not in the same level. But when we talk about independent events, say A and B, if they're independent, then the occurrence of event A is not affected by the occurrence of B. Okay, and likewise, the occurrence of B is not affected by the occurrence of A. Okay, but they could happen together. Okay, they could happen at the same time. Whereas for mutually exclusive, if one happens, the other would not happen. And in this case, the probability of the intersection of A and B equals to the probability of A times the probability of B. So let's review some examples. So for the first one, so for example, if I'm choosing a card from a deck of cards, picking a diamond king and picking a diamond queen, okay, these two events are mutually exclusive because these two cannot happen together. If I'm just picking one card from the cards. Well, of course, when I mean choosing, it means that you're picking randomly, okay? You cannot do that selectively, okay? It's got to be all random. So in this case, if you're choosing a red versus choosing a black, okay, these two events, not only are they mutually exclusive, they're also complementary, meaning that these two together will add up to the whole universe. Okay, so either red will happen or black will happen. Okay, and of course, if you consider this third example, choosing a number card from a deck of cards versus choosing randomly a diamond card from a deck of cards, these two events are not mutually exclusive because, as you can tell, there is overlaps. For example, a diamond 2, okay, satisfies both, right? So it's an overlap, so they're not mutually exclusive. Now let's say I have a box of balls, and each ball is of a different color. And event A is I'm randomly choosing a ball from the box, and it's a red ball. And event B is you choose another red ball from in a second draw, okay, but the key is it's a replacement, meaning that after you're done with event A, you put whatever ball you chose and you put it back, okay. And so these two are independent events, okay, because whatever happened in event A does not affect event B or vice versa because of the word replacement. All right, so if it's without replacement, okay, meaning that after you've picked the first ball, okay, whatever is red or yellow or whatever, you don't put it back into the box, okay, then these two events will not be independent, okay. because say in the first draw you've picked a red ball, and that means in your second draw you have one less red ball to choose from, right? Okay, so your probability will be different from event A. Okay, so it depends what your first draw is, right? Now here's some tricky part if you compare the two concepts. Mutually exclusive events, if they're both non-zero probability, okay, they're never independent. Say for example, if I know that probability of A equals to 60%, if they are mutually exclusive, then we know that probability of B must be less than or equal to 40%, right? It cannot be 50 because there's no overlaps. That means we are given some kind of information about the probability of B. Okay, so in other words, they cannot be independent. So mathematically, that also proves that, okay, so if they're mutually exclusive, then the intersection, okay, the probability of A and B must equal to 0, right? However, if they're independent, that means the probability of A and B must equal to the product of probability and A and the probability of B, okay? They both are non-zero, okay? Which means that these two cannot happen together, right? So there's a contradiction between these two statements. If you say A and B are mutually exclusive and independent at the same time, okay?